So, therefore, the next section, what are F53's assumptions? And first, the first type. And you will see the difference to the second type when I come to the second type. Friedman explains immediately after the given quote that I just mentioned, a hypothesis is important if it explains much by little. This is, if it abstracts the common and crucial elements from the mass of complex and detailed circumstances surrounding the phenomenon to be explained and permits valid predictions on the basis of them alone. This is my italics. So this is what he writes about these assumptions. And the physical example is the falling ball, whose behavior is explained by recourse to gravity alone. That is, in the law of free fall, counterfactually set constant along the ball's trajectory. The gravity is in the law of free fall, is by the way counterfactually, Friedman doesn't mention that, but that's the case, is set constant. In truth, it's not constant along the free fall, but this is an approximation. And to know other forces or other specific properties of the situation. So, what does he say by that? An economic example is the effect of a tax increase on retail prices of cigarettes, which can be explained by recourse to the competition of firms alone, thereby abstracting from all other factors. So what he's basically saying is, look, we use in such theories, we abstract from many things and put emphasis on one factor, and that's the essential factor for the phenomenon we are investigating. Right? This is what he says. Friedman continues, to be important, therefore, a hypothesis must be false in its assumptions. Why? Because it abstracts from so many things, right, that are there in the world, and therefore descriptively, what I'm saying with this abstraction is something false. It doesn't get the richness of reality. The falsity consists in idealizing the most relevant factor, right? So in the case of free fall, the most relevant factor is gravity. But gravity is not described as it really is, because gravity changes independence, whether you from the distance from the center of the Earth. That's the distance. The distance changes along the fall. So if you really calculate, gravitation is not constant. The law of free fall assumes it is constant, right? But it's not constant. It's false, right? It's definitely false. Gravity changes, and we can measure it to very, very high degree. It really changes. So that's false. The law of free falls. The law of free fall is false. Gravity is not constant. Not even 3 centimeters. Not even 1 centimeter. Gravity changes, and of course, it's constant gravity in the case of free fall, and perfect competition in the cigarette case. There is no perfect competition. Right? Of course there isn't. But for this particular case that Friedman has in mind, perfect competition does the job of explaining what's going on, like the law of free fall does the job of explaining what's going on. So there are two things. The falsity is idealizing the most relevant factor and abstracting from all other factors that are part of the real situation. So as a description, what you're doing when you do that step, you're making really bad mistakes. You're idealizing something, meaning you describe it falsely, and you omit many, many things that are also relevant, which is also false. They are there, right? So you're making really big mistakes, okay? And Friedman continues, the relevant question to ask about assumptions of a theory is not whether they are descriptively realistic, for they never are. Right? That's the point. Of course, gravity isn't constant, and of course there is friction. Of course it's false. But the point is whether there are sufficiently good approximations for the purpose of had. Why sufficiently good approximations? Meaning that if I make, in the case of free fall, whether the predictions of the distance as a function of time is good enough. Right? Whether for that purpose the assumptions are good enough, although they are fundamentally false. Friedman continues, and this question can be answered only by seeing whether the theory yields sufficiently accurate predictions. So you can only judge whether your abstractions and omissions, whether they yield good predictions. That's the only way you can judge them. And this is now the point. We come now really to the core here. In a concrete situation, or a concrete situation is treated as if only a few, even idealized factors were present. Right? Free fall, just gravity and idealized constant gravity, which it isn't, right? Or perfect competition, as if nothing were there, right? Competition, no other factors, no policy factors, nothing, right, were present, which is descriptively false. And this procedure is justified by sufficient predictive success. So you are brutal, in abstracting and idealizing as long as your predictions are good. But the basis is really abstraction and idealization. Okay. Now, to describe that somewhat abstractly, a concrete complex situation S is treated as if it was a drastically simpler situation S star. Right? So the situation, this object falls down there, that's the real S, and the idealized situation is drastically simpler. Clearly then, as a description of S star is utterly false. So if I describe the falling of this object as the falling of a point particle in vacuum with constant gravitation, is utterly false. Right? Is really utterly false. But if I use it, I get the right predictions in this situation, right? Not if I jump from 2 kilometers, not if this is a feather. But for that object, in this situation, it works, right? So as a description, S star is utterly false. The use of S star instead of S is justified by the fact that it can be scientifically treated. So you write down the law of free fall, and you can immediately calculate. That's very simple. For example, it can be exactly described in mathematical terms, and it yields sufficiently good predictions. That's the case for the law of free fall. That seems to be the case for the cigarette case, where you can treat the firms as if in perfect competition if you have taxation increased from the government. And the point is then it's a very specific falsity that he's in mind, right? And this is what people don't get, or many people don't get. They just say, oh, you can use any falsity. No, that's not what Friedman says. The specific falsity of S star may be called descriptive falsity due to abstraction and idealization. That's the point. The abstraction is, you say only one factor counts, right? The other forces, I don't count them. And that one factor I don't describe as it is, but I idealize it, right? Perfect competition or constant gravitation. So you make intentional falsities, and you control the falsities then by the predictive power that the hypothesis generates. So this is the first type of these falsities that Friedman has in mind. But of course, you have to extract them, and it's complicated. You have to read that very, very carefully. He never says that, and had he thought a little longer, he could have said it, possibly. Anyway, so in this particular case, the first type, the degree of descriptive falsity of S star can be decreased by adding corrections, which partly revert the abstraction and idealization. So this is idealization in economics. It's a big topic in philosophy of economics, has been discussed in many contexts, and that is then called de-idealization. Also in physics, you have exactly the same. You make, so for instance, the law of free fall, you can idealize and say, okay, let us add a term for the friction. Right? And then you add a term in the differential equation for the friction, and then you de-idealize by making the description a little more realistic. Right? It's still then unrealistic for certain reasons. Say you don't have the radiation pressure by the light, that's there, whatever. So the point is, you don't see why this is relevant, this last passage here, because that's different in the second type of assumptions, right? So, but in this particular type, they can be de-idealized. And it's a specific falsity, descriptive falsity, due to abstraction and idealization. Example: free fall, add friction, make gravitational height dependent, etc. Right? Then you first make it really false, and then you can bring it nearer to an accurate description of reality by de-idealization. All right, and that's good for now. I said there was a first type. There were two separate types or kinds of assumptions. And the first type I tried to describe, and I got that from the examples. This is, by the way, very often a very good way. If you want to understand an author and you don't really understand what's going on, go to the examples, because then from the examples you may suck out what the author really has in mind, even if he or she hasn't formulated that abstractly. So this is how I did it, and then many other authors I do exactly the same. Read the examples and then try to get into the head of the author, and then you may understand what the author has in the back of his mind, possibly not perfectly expressed in the abstract description. So the problem is that Friedman also uses, and this is now the new stuff in case you're just waking up. This is the new stuff in this lecture. Friedman also uses another method to generate descriptively false but scientifically fruitful situations as star. Right? Without explicitly, unfortunately, without making the difference to the first type explicit. And that, of course, contributed to the confusion about F53. By the way, now, the point is, what's the difference between the second way of generating false assumptions? In the second way, S is not only simplified by abstraction, that's also taking place, but then is something really dramatic happening. A relevant factor F in S is substituted. So you take it out and substitute it by another factor, a qualitatively different factor F star, that is unreal, that doesn't even exist. Right, in reality. So you're really falsifying, you make it really very, very false, the assumptions you're using. But a different factor F star, that's unreal, and that yields situation S star. Now you'll ask, wait a minute, is that a scientific procedure? Well, let's see, let's look at the examples and look at then the justification why he's doing that. So here are Friedman's examples. The first one was the leaves of the tree, which are treated as if they individually sought to maximize the amount of sunlight. Right? So you treat the leaves of the tree as if they had an individual will and calculational abilities to calculate, whoops, where I am going in view of the other leaves where I'm getting optimal sunlight. And that's, of course, that never happens, absolute nonsense, of course. But he says that is a good idea. And what he also sometimes says, by this procedure, you may summarize a lot of experiences you have with trees. Right, in the leaves on trees. So this is completely unreal, but it has some merits. Okay, let's go to the other examples to get more feeling how that works in economics. Well, first another one, the expert billiard player who is treated as if she solved the relevant differential equations. So and that is then F star. Now the point is, if you want to predict the behavior of that billiard player, expert player, you can do it by saying, okay, I solve the relevant differential equations for the path for the orbit of the billiard ball, and then I look whether the expert billiard player does that, what the physics tells me, what the optimal way of the ball is. And if that substitution is okay, then the result will be the same, right? So it looks as if the expert billiard player calculated that on the basis of the differential equations. Of course, she doesn't do that. But the point is, if she behaves as if she calculated, then you can, for predictions, use that substitute. Right? You say, if I want to predict how this expert billiard player plays the next ball, and I calculate on my computer to solve the equation and say, oh, the optimal way to do it is this, that, and then it reaches that ball, and then happen this. And then if you see that this is exactly what the expert billiard player is doing, then you can say, of course I can predict her behavior. You do not explain her behavior by that method, right? Because you're using a substitute, so you can't explain it because you don't know how the expert billiard player is doing it. But if you're only interested in the prediction, that's wonderful. Right? So this is one of the reasons, by the way, this is also not stressed in the paper, that in many cases in economics, it's really the emphasis is on prediction and less on explanation in some cases. So in this particular case, you see that, because if you work with that substitute, then you can predict, but you cannot really explain the behavior, right, in the same way. But if you don't need that, so if you want to predict consumer behavior after a certain policy change, that's good enough if you have something like that, right? Then you're not really interested in the explanation because you want to have a handle of what the consumer will do when I make this or that policy change. So this is completely legitimate. One should only be aware that the instrument one is using is a good instrument for prediction, possibly a good instrument for prediction, but possibly a very bad instrument for explanation. Okay. Now, here we are now at the economic examples. Firms are treated as if they were seeking rationally maximal expected returns. That's F star. So you treat the firm as if it was really calculating on the basis of economic theory. expected utility maximization. You calculate that, and then it may be the case, if you apply that reasoning to the behavior of the very best firms in the market, that their behavior indeed is the same as if they calculated, right? But you don't really know how the managers are doing it, whether they're doing it out of their gut feelings or whatever they do, or ask their wives or husbands or whatever, you don't know it. But if that is possible to predict their behavior, then you say, okay, that seems to be a very good substitute. So the point is here, in the background, that's all in, one only has to read it. I mean, it's in Friedman. I didn't invent that, right? The substitution of f by f star is motivated by a plausible claim that in the given situation, f star has approximately the same effect as f, but it's easier to handle, right? For the economist, easier to handle. So you say, okay, I treat the expert billiard player as if she was rationally calculating, and then I've got the instrument to predict what she's going to do, right? I don't know how she's calculating it, but I can calculate it by physics and then predict what she's doing. So, and what's that it's motivated, and now there is a motivation that you say, yes, it's not stupid to make this substitution, and you must have a motive for that. And the claimed effect equivalence of f and f star, you know, the effect is the same, expert billiard player doing whatever she does, and I calculating it, is made plausible by a certain theory that connects f and f star. You have to have that. Right? In order to make this connection plausible, you have to have some sort of reasoning. And the reasoning is a certain theory that connects f and f star. And in the three examples that Friedman is using, the connecting theory is a sketch of selection theory. So in biology, the so-called neo-Darwinian theory of evolution is also called selection, because the main factor, explanatory factor, is selection. Right? So you have a certain population, and then some individuals are selected, have a selective advantage in comparison to others. So this is selection theory. So whenever you have a situation of a population and not all the individuals are equally successful, then under certain circumstances, the more successful ones are positively selected and the other ones somehow disappear. That's, of course, almost a caricature of selection theory, but that's really the core there. There is genetic variation, random fluctuations of all sorts, and then there is selection. There are other mechanisms as well, but that's the basic thing. So what he says is, so we have, in the case of the leaves on the tree, there was selection theory, biological evolutionary theory working, because only trees that optimized were finally those surviving species of trees. In the other cases, it's so that the selection processes are societal, right? So only those firms in the longer run stay alive in the market who optimize, because those who don't optimize are then overpowered by those who are better on the market, right? They make more profits. The point is, however, so the optimizing, well, that's the idea of selection processes, of selection theory, that the optimizing effects of selection processes on F suggest that it results in a F that is as optimal as an optimal rational choice process, F star. So in biology, for instance, you have different sizes of ants, and the sizes correlate with the functions. In ants societies, ants have certain functions, and they have different sizes. One of the same, I don't know what it's called, flock, one of the same group of ants. And then what people have done, for instance, they have calculated what the optimal size of an ant would be given a certain function. So those who cut leaves have a different sort of function than those who work inside, and do something with the eggs. And then people have calculated what would be the optimal size from the energy turnover of, say, these ants who cut leaves and ants with other functions. The result was that indeed evolution, natural evolution, has more or less optimized the size of these ants. So when you calculated this was very close, that the optimal size concerning the energy turnover was quite close to what you could see in nature. So selecting processes are processes in nature that indeed optimize with constraints. Of course, there are constraints, they can't do everything. So with constraints, they optimize different treats of individuals belonging to a species. It's got important constraints. So, for instance, one of the most fascinating constraints I find is that if you look at insects, there are very many different numbers of pairs of legs, right? From 4 legs to whatever, 6 legs and 1,000 legs. And that is an evolutionary road that apparently for vertebrates is not open. All the vertebrates have only 4 extremities. And of course, you can calculate that having 6 legs or something for running has certain advantages, which the insects exploit. But apparently, obviously, the vertebrates cannot exploit. So there are some genetic constraints such that no variation could be produced for vertebrates with 6 legs, apparently. This is what we can see. Anyway, so optimization in selection theory is always under constraints. So it's not limitless. So it's under constraints. So, but the point is, if you know what these constraints are, and then you may be able to calculate a priori an optimum. Right? And that is, of course, in the case of economics, is, of course, the rationality that's inbuilt in expected utility theory. Right? You optimize your choices according to the utilities, and there you go. And then you can, of course, predict if there are firms that are optimally adapted to the market, that they will be doing what rational choice theory would suggest. Is there a question? No. Okay. All right. So the final justification, however, for the substitution of f by f star in S star is that it yields sufficiently good predictions for S. Right? This is still speculative when you say, yeah, the best firms, they will be, optimal, blah, blah, blah. You don't really know that. You would say, yeah, there's selection pressure, but you don't know what the constraints are and what not. So this is what Friedman says. So the final justification is that it's sufficiently good predictions. And this is the stress on good predictions, that they have the final say. Because the experience in all the sciences, including economics, is you may argue as plausibly as hell concerning thousands of things. And you say, oh yeah, that must be like that. And then you test it experimentally, empirically, and then you find out it's not like that. Right? It's always the same, and it's been for centuries that experience. You may have so fantastically good arguments for something, and then you find nature does not behave that way. So you've got to test it experimentally. And that's the ethos you find in all the empirical sciences. So now, of course, in many, many branches in economics as well, but of course in biology and chemistry and physics, of course, there's trivial almost, that if you have a certain claim, you've got to give an empirical argument in the end, right? That may take a while until we reach that. If it's very sophisticated theory, then you have to work out what the consequences are, the possible empirical consequences, and that may be awfully difficult. But in the end, it's really the experimental results, so more carefully, the empirical results. There may be observational or experimental. And this is, of course, the same what Friedman does. He says, yes, it may be as plausible as hell, but that's not enough. It's just not enough. Plausibility, we know that, is not really a perfect guide to truth. You've got to do it experimentally. And then, of course, clearly as a description of S star is false, as in the assumptions first type, but it's a different kind of falsity. In the second kind, the specific falsity of S star may be called descriptive falsity due to abstraction and substitution. Right? You're substituting a real factor by an unreal factor. In contrast to the first case, the transition from S to S star cannot be gradually reverted by adding corrections. Of course not, because F star is a qualitatively different substitute for F. Right? If you substitute the expert billiard player by a program that solves the differential equations, you cannot, by refining that, come to the real thinking processes that happens in the expert billiard player. They just, by experience and feeling and whatnot, I don't know how they're doing it, but anyway, there's no way to reaching that by, adding more terms in the differential equation. No, that doesn't work. So they are qualitatively different, and they remain so. So you cannot bring them nearer together, but that's really not important. That's not part of the game, right? So the problem now of understanding F3, or one problem of many problems, is that when Friedman speaks in general about false assumptions in economics, he mostly refers to descriptive falsity due to abstraction and idealization, and not to descriptive falsity due to abstraction and substitution. And once you realize that, you get confused, because then the examples Friedman is using do not fit his general talk about that. And only if you find out, well, he's using two different sorts of things, and you analyze them and see what the arguments are, then you can get into this maze that Friedman produces here. Now, it's very important, and that I've never seen in the literature anywhere. It should be noted that also physics contains not only descriptive falsities due to abstraction and idealization, that's the first type, and the law of free fall was the example. That's the only physics example that Friedman has. He describes it not completely correctly, but anyway, it's good enough. But there are also in physics descriptive falsities due to abstraction and substitution, second type, and they are very important. The building of the first atomic bomb was based on such descriptive falsities of the second type. Here's the example. There is a so-called, an atomic nucleus, according to what we know, is composed of particles, especially protons and neutrons, and some other stuff, glue stuff, and so on. And uranium has more than 200 of those particles, and they are just these things that are held together by nuclear forces. Now, there was a model invented in the 1930s, the so-called liquid drop model of the atomic nucleus. And that model counterfactually assumes that nuclear matter is an incompressible continuous liquid with surface tension and viscosity, as opposed to being composed of discrete particles. So you assume that the atomic nucleus, of which you know it's composed of particles, you just say as a physicist, no, I treat it as a liquid incompressible, right, as most liquids are, and with a surface tension. What you see is when in your water, at the edges, the water goes up there. That's due to surface tension, and why insects can walk on water. And we have viscosity, so it's more syrup-like and not a perfect fluid. So you assume that. The corpuscular structure of the nucleus is thus substituted by a continuous liquid. Right? And you do that willfully in physics. And I come back later to the consequences of that. Now, in a strict sense, this is not an approximation to the real situation. Because when you talk about an approximation, you usually have in the back of your mind that you can improve it by adding corrections. So I do it approximately, and then I can bring it nearer by adding corrections, and so on. So this is not really the case here, but it's a qualitatively counterfactual assumptions. And physicists are very free there using such stuff. So you treat something, you say, oh, that's an atomic nucleus. Oh, let's try, I treat it as a liquid. Let's see how good it works, right? Well, now is a problem because physicists talk in that way still as an approximation. You say, I approximate the corpuscular structure of the nucleus by a liquid. Physicists talk that way. It's loosely talking, but in a sense, it's not really an approximation. Well, in another sense, it is, because if the particles get smaller and smaller and smaller and smaller, which they don't, then that would somehow approximate a liquid. Anyway, but this is really words, and physicists are generous there, they say, and every physicist understands that. Okay. And the point was, what I mentioned, this model was invented in the mid-30s, and in 1938, two physicists, Niels Bohr and Archibald Wheeler, found out that with that model, one could describe nuclear fission, right? Because these liquid drops, if you give them a push, by pushing a particle into them, they start oscillating, and they may oscillate as strongly that they decompose into particles, which is exactly what happens in the atomic bomb. And on this model, the first two atomic bombs were built, right, that were used, the different types of atomic bombs. So this is not just, playing around without consequences. This is real physics with world-shattering consequences. Until today, right, that Russia has atomic bombs is a very, very important factor in today's conflict. So, and when you ask physicists, why are you using such a crazy model, treating an atomic nucleus as a liquid, they say exactly the same, what Friedman says about such models. The model is good enough regarding its predictions for the given purpose, right? So the liquid drop model is good enough to predict the possibilities of nuclear fission, because you simulated that by the oscillation of a liquid. I mean, it's crazy if you think of it, but it works. And then physicists say, wonderful, right? We can predict it, we have nothing better. And this is the next thing. An alternative model that is predictively better is not available at the time of the introduction of the model. So this is exactly the case. So if you tried to calculate the properties of a nucleus in 1938 on the basis of its real structure, namely composition of particles, you couldn't calculate anything. You didn't have the physics. It took 15 years or something. In the mid-50s, or 60s even, people started seriously then treating atomic nuclei as really a composition of particles. They weren't able before. And only then, in the mid-60s, I think the first results came out that were better than the predictions of the nuclear drop model. So then it was, of course, a reason to switch. But if you don't have that reason, you say, well, why? We substitute and we can calculate and predict something we cannot really explain, right? But we can predict. And if prediction is the important thing, then that's good enough. So now we can understand, now I'm bringing all these things together, now we can understand why F53 uses scare quotes around assumptions. If you look, and I did then go to the internet and look in the different lexica, assumptions are facts or statements taken for granted or plausibly assumed to be true without strong epistemic grounds. For instance, a proof. So that's what you usually do. So if you say, look, I assume now that the crime rate in Switzerland has slightly decreased, then this may be somehow plausible. You may have not measured it, but so when you say, I assume that it has decreased, that means you take it for true, but you say, I assume it, I don't really have the latest data. So for instance, let's take this example. So say it may have decreased, a certain, all over, all crimes have decreased within the last 5 years, so until 21, and then you say, what is your assumption about the development of the crime rate in 22? And then you may say, well, I assume that will further decrease because I didn't see anything what could break this trend, right? So you don't have a strong argument, but you think it's true, but you don't have a strong argument, you don't have the data. This is what we call an assumption, right? It may be plausible assumption, or someone might say, no, that's an implausible assumption. And then you say, okay, let's drop this implausible assumption. There's no assumption anymore, right? So this is how we usually use the term assumption, facts or statement taken for granted or plausibly assumed to be true, without strong epistemic grounds, for instance, a proof or something, or data. By contrast, F53 scare quote assumptions do not imply an epistemic commitment to truth. On the contrary, they are intentionally false, right? And therefore, of course, the unquoted term assumption doesn't fit. There are not assumptions in the normal sense. For instance, in F53's view, Homo economicus is in general false. He knows that, and every economist at the time knew that, but a sometimes useful ansatz for some problem situations, right? So that's the point, and this is why he says, well, the term assumptions doesn't really fit. Now, in very short, you can put it this way. Normal assumptions are epistemically committal. Scare quotes assumptions are non-committal, right? By articulating, normally if you say, my assumption is this and that, then you say implicitly, yeah, I believe this is true. But Friedman's assumptions don't have this property. On the contrary, he knows that they are false, right? But he uses them. So he doesn't have a term for that, and then he uses assumptions with scare quotes, but never explains really what he means, unfortunately. So, the discussion of assumptions so far referred to the material in sections 1 to 4 of 53, which Friedman denominated as abstract methodological issues. Right? There he says abstractly, abstract meaning not only concerning economics, but more abstract, possibly concerning more sciences. And of course, in the back of his mind, he thinks that's also adequate for physics. And then in section 5, he turns, as the title says, to some implications for economic issues. So that one has to see. There's this abstract part, and then he turns to economic issues. And here he discusses a special aspect of assumptions that's relevant in economics. And here we get final clarity on what Friedman means by assumptions in scare quotes. So far, we only know, okay, they're intentional falsities. The falsities are generated such and such, first kind, second kind. And then he's getting more concrete and he's going to tell us in which way these falsities of the two kinds are generated in economics. All right.